Decode Ways. Imagine this: you're in a high-pressure tech interview, and you're handed one of the trickiest DP string problems out there, Decode Ways. This Pattern Mastery 100 staple isn't just a test of coding, but of true problem breakdown and logic. Did you know that over 40% of candidates get tripped up by edge cases with leading zeros or multi-digit decodings? If you can master Decode Ways, you'll be ready for any string or DP problem thrown your way. So let's crack it together. Here's the breakdown. You're given a string of digits, like 102,213, and each digit or pair of digits can map to a letter, 1 to A, 2 to B, 26 to Z. Your job? Count how many ways you can decode the string, following those rules. A 0 on its own is invalid, but 10 is valid since it maps to J. What are all the possible decoding paths? Now, let's assess the challenge. A brute force recursion would explore every way to split the string, but it's way too slow. We need dynamic programming. For each position in the string, we'll store how many ways we can decode up to there. Key edge cases? Zeros. 0 isn't a letter, but 10 is valid. We need to handle both single-digit and two-digit decodings. Here's how we'll structure it. Set up a DP array where dpi is the number of ways to decode the first I characters. Initialize dp0 equals 1, empty string is one way. For each position I from 1 to n. If si1 is valid, not 0, add dpi1. If si2:i is between 10 and 26, add dpi2. Approach: recursion with memoization. Time complexity, on. This line defines the solution class. In Java, every method must live inside a class. So this is simply the container for our decoding logic. Here we create a map called memo. This is used for memoization. The key represents a position in the string, and the value represents how many valid decoding ways exist starting from that position. This helps us avoid recalculating the same work. This is the main method. It takes a string of digits and returns the total number of ways it can be decoded into letters. This line starts the recursive process. We begin decoding from index 0, meaning the very first character of the string. This closes the num decodings method. This defines a recursive helper method. The parameter I represents our current position in the string, basically, where we are in the decoding process. We store the length of the string in n. This makes our boundary checks clearer and avoids repeated calls to length. This is a base case. If we've reached the end of the string, it means we found one valid way to decode everything, so we return one. Pause. This represents a successful decoding path. If the current character is 0, decoding is invalid because no letter maps to 0. So we immediately return 0 to stop this path. If we're at the last character and it's not 0, there's exactly one way to decode it. So we return 1. Before doing any recursion, we check if we've already solved this position. If the result is in memo, we return it right away. This is what keeps the time complexity linear. Here we explore the first option. Decode one digit and move forward by one position. The result of that recursive call is stored in arrays. Now we extract the next two characters and convert them into a number. This lets us check whether decoding two digits together is valid. If the two-digit number is between 1 and 26, it represents a valid letter. In that case, we add the number of decoding ways that come from skipping two characters. Pause. This is where branching happens. Once we've calculated the total number of decoding ways starting at index I, we store it in the memo map so we don't recompute it later. Finally, we return the computed result for this index. This closes the recursive helper method, and this closes the class. Final wrap-up. And that's how this algorithm works. It first handles base cases and invalid digits, then recursively explores one-digit and two-digit decoding paths while caching results to avoid repetition. Efficient, simple, and elegant. Test case check. Decode ways using recursion plus memo. Let's test our function using this input. 12. This string represents an encoded message where each digit or pair of digits maps to a letter, 1A, 2B, 26Z. Here's why the solution works. We use recursion to explore every valid way to decode the string. First, we try decoding one digit at a time. Then, if the next two digits form a valid number between 1 and 26, we explore decoding them as a pair as well. Memoization ensures we don't recompute results for the same index more than once. And that's exactly what our program outputs, too. This confirms that the recursive plus memoized approach is working correctly and matches the expected result. Wrap up. So, our implementation is correct. The algorithm successfully counts all valid decoding paths by exploring single-digit and double-digit options, efficient, accurate, and reliable. Approach: bottom-up DP. Time complexity, ON. This line declares the solution class. It's simply the container that holds our decoding logic. Here we define the num decodings method. It takes a string of digits and returns how many valid ways that string can be decoded into letters. This line stores the length of the string in n. We'll use this value often, so saving it avoids repeated calls. If the string is empty, there are no ways to decode it, so we immediately return 0. Here we create a dynamic programming array called dp. Each position dpi will represent the number of ways to decode the substring starting at index I. This sets the base case. An empty substring has exactly one valid decoding, doing nothing, which allows previous calculations to work correctly. This line handles the last character. If it's 0, it can't be decoded on its own, so the count is 0. Otherwise, there's exactly one way to decode it. This loop walks through the string from right to left. Since each position depends on future positions, filling the table backward is the correct approach. We still only loop once, so the time complexity remains ON. If the current character is 0, there are 0 valid decodings starting here, because 0 can't represent a letter by itself. This opens the branch for characters that can be decoded. Here we count the number of decodings that treat the current digit as a single letter, and then move one step forward. This line takes the current digit and the next one, combines them into a 2-digit number, and converts it into an integer. If the 2-digit number is between 10 and 26, it represents a valid letter. In that case, we add the number of ways to decode the remaining string starting 2 positions ahead. This closes the conditional block. This closes the loop. After filling the dp table, the first cell contains the total number of ways to decode the entire string, so we return it. This closes the method. And this final brace closes the class. Final wrap-up. And that's how this algorithm works. It first sets up base decoding cases at the end of the string, then works backward combining 1-digit and 2-digit decoding options to build the final answer. Efficient, simple, and elegant. Test case check. Decode ways using bottom-up dynamic programming. Let's test our function using this input. 226. This string represents an encoded message, where each digit or pair of digits corresponds to a letter from 1A through 26Z. Here's why the solution works. We fill a dp array from right to left, where dpi represents the number of ways to decode the substring starting at index I. If the current digit is 0, it contributes 0 decodings. Otherwise, we add dpi plus 1, decoding the current digit alone, dpi plus 2, decoding the current 2 digits together if they form a number less than or equal to 26. And that's exactly what our program outputs. 3. This confirms that our bottom-up dp approach is computing the decoding count correctly. Wrap up. So, our implementation is correct. The algorithm successfully counts all valid decoding paths using an efficient dp table, reliable, accurate, and performant. Decode ways. Let's do a recap. So, how do you turn a string of numbers into letters, and how many ways can you do it? Decode ways is one of those deceptively simple dynamic programming problems that really tests your logic under pressure. Once you understand its structure, though, it becomes one of the most elegant DP challenges out there. Breakdown recap. We started by understanding the core problem. Given a string of digits, each single or double-digit number can represent a letter from A to Z. The goal is to count how many valid ways you can decode the entire string. But there's a catch: zeros can't stand alone, which makes handling combinations like 10 or 20 critical to getting the logic right. Assess recap. We compared the brute force recursion with dynamic programming. Recursion explores every possible split but grows exponentially. DP, on the other hand, builds the solution step by step by remembering how many ways we can decode each prefix. That's the key to handling overlapping subproblems efficiently. Structure recap. Our plan was clear. We used a DP array where each position represents the number of ways to decode up to that point. For each digit, if it's valid, not zero, we carry forward previous counts. If the last two digits form a valid pair between 10 and 26, we add in the count from 2 steps back. By the end, the final value tells us the total decoding count. Implement recap. We implemented this logic in Java and ran it on LeetCode without any errors. The DP solution worked efficiently in ON time and space, and we even noted that it could be optimized to O1 by using just 2 variables. Check recap. After running our test cases, the output matched perfectly with expectations. The DP table captured every valid decoding path, confirming that the logic worked for both regular digits and tricky zero cases. Closing insight. The big takeaway? Decode Ways teaches the heart of dynamic programming, breaking big problems into smaller overlapping parts. Once you master that pattern, you'll recognize it everywhere, from strings to sequences to any problem that builds on past results.